In the last section we changed gears a little bit. We started talking about antiderivatives, which is essentially the opposite of differentiation. You're given a function, and usually what you'd want to do is you'd want to differentiate it. But now we're asking a new question. Instead of wanting to differentiate this function, we want to find another function whose derivative gives us the original function. So it's sort of a different question there, and it's called antiderivatives because it really is the opposite of differentiation. We'll see very soon over the next two sections that that concept ties very closely in together with something called integrals. And because of that, we sort of just we jumped ahead and immediately introduced this integral notation, and I told you that finding an antiderivative is the same as finding an integral. So we introduced this integral notation, and the truth was in the last section is we couldn't integrate many functions because there aren't many antiderivatives that we know of. We just had this very simple list. I gave you a list last time. We can integrate things like x to the n, 1 over x, e to the x, and that was about it, right? So not many functions that we could integrate. So if I gave you a more complicated integral to compute, your goal was to basically do some algebra, manipulate it somehow so that it looked like the very simple list of functions that we had, this very short list, right? If you had something complicated, you wanted to manipulate it so it looked like x to the n or e to the x or something like that. Well, that won't get us very far. Like I said, there's really sort of two halves to calculus. You've got differentiation and integration. If you ever go on to a Calculus 2 course, the first basically half of Calculus 2 is dedicated to more advanced techniques for finding integrals. We won't do all of that, but I will introduce one more technique that's more advanced than what we were doing last time, and it's this idea of, okay, if I can't use just algebra to manipulate my integrand, remember the integrand is the function we're integrating. If I can't use just simple algebra to manipulate it to a simpler looking function, one of our few in the list that we have, maybe I can make a substitution. And the best way to teach this, the best way to show you how substitutions work is just to teach it by example, I think. So we'll jump straight into examples here. So here's our first example. Find the integral, so antiderivative of, find the integral of 2x times the square root of x squared plus 1 dx. So if you look at this, you'll see this is a pretty complicated looking integrand, the function on the inside here. It's a product for starters, is 2x times the square root. And the square root's pretty complicated because this is a composition of functions. I've taken x squared plus 1, and I've composed that, I've thrown that into a square root function. So what types of things could we integrate last time? Again, just things like x to the n and 1 over x, e to the x. Well, I don't see any way to do algebra to make this look like anything involving just x to the n, right? Polynomials, basically. So my idea is let's make a substitution. I'm going to tell you what the substitution is going to be. Essentially, I know how to work with square root of x. Right? Square root of x is fine, that's x to the 1/2. If it was just square root of x, we'd be golden here. But I can't work with square roots of anything else. I can't have these compositions going on. So I'm going to try to simplify the inside of the square root. I'm going to make a substitution. I'm going to say, let u be the whole inside of that square root. Let u be x squared plus 1. So I'm going to make this substitution. The inside of this is going to become u. But what I want to have happen is I want to turn everything into u. So I'd still be left with 2x on the outside. That doesn't make much sense. 2x times the square root of u, and then a dx. Well, dx tells me I'm integrating with respect to x, but what I want to do is turn this into a function of u. So hold on. If u is x squared plus 1, what is the derivative of u with respect to x? du over dx is what? It would be derivative of x squared plus 1 is just 2x, right? This is where the Leibniz notation comes in. We haven't really had to do this throughout this course, but Leibniz notation is extremely suggestive of what's going on here. Up to this point, you should have always read this as a derivative. It just means the derivative of u with respect to x. But the Leibniz notation is very suggestive of the fact that this is actually a ratio of two things. It's what's called a ratio of two differentials. And I can algebraically work with this as literally a ratio, meaning I can multiply both sides by dx. So this means du, if I solve for du, is 2x times dx. Well, that's really nice, right? Because this is going to become square root of u. But what's left over? Left over, I have 2x times dx. I have 2x times dx. What is 2x times dx equal to? It's equal to du. So that is du. Meaning under this substitution, this integral has turned into the integral of just the square root of u, and 2x dx is du. And that's a much easier integral, right? I can integrate the square root of u, no problem, just by turning this into u to the 1/2 du. And that's like x to the 1/2, except my variable is called u here. And integrating that's no problem from last time. Right? From our very simple list of functions last time, I can work with x to the 1/2 or x to the n. So the integral of this would be u to the raised to the power by 1, 3/2, divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3, right? So dividing by 3/2 is the same as multiplying by 2/3. And I've forgotten to do one thing here. I need to write plus c. And I want the most general antiderivative. So there's one more thing left to do, which is I didn't start with a function of u, I started with a function of x. But what I can do is I can back substitute. I know what u equals. U is x squared plus 1. So if I want to go back to x, this will be 2/3 times x squared plus 1 to the 3/2 plus c. And there's my answer. I claim that this is an antiderivative for that original function. Now, I haven't mathematically justified why I'm allowed to do any of this stuff, why this works, and I really won't. But what we can do is we can check that it did work. Right, if I'm claiming that's an antiderivative for this original function, let's go ahead and differentiate it. So let's check this. The derivative of 2/3 times x squared plus 1 to the 3/2 plus c is going to be what? It'll be 2/3 times the derivative of this function of x. So I've got a function of x plugged into a function that raises everything to the 3/2 power. So special case number 1 of the chain rule. Power comes out front. 3, that's a funky looking 3. 3/2. Inside stays the same. Power lowers by 1. 3/2 minus 1 is 1/2. And then the second half of the chain rule says now I multiply by the derivative of the inside. So the derivative of x squared plus 1 is 2x. Plus derivative of c, which is plus 0. Lots of stuff cancels here. 2, 2, 3, 3. And I'm left with 2x times, I'll go back to square roots here, square root of x squared plus 1. Which is exactly our original function. So indeed, this is an antiderivative for this function. So this process of substituting worked. It worked really well for us. It allowed us to find this much more complicated antiderivative than we could possibly do before, because there's no way to just do a simple algebraic manipulation on this to turn this into one of our very few functions in our list that we know antiderivatives for. But substitutions can be really powerful. And I've told you there's really no such anti-product rule, anti-quotient rule, anti-chain rule for integrating, so this is what makes integration so hard. But what the substitutions are really trying to do is they really are somehow trying to reverse the chain rule. So that's what's happening behind the scenes. Don't worry too much about that. We'll do more examples. The more examples we do, the better you'll get at this. So here's our next example. It's the integral of x cubed times e to the x to the power 4. So again, a pretty complicated looking function. No way to just algebraically manipulate this into something simpler. So I'm forced to, now I'm going to try to make a substitution. And the reason I want to go through so many examples here, the reason you'll get better as we do more examples, is because choosing the right substitution is a bit of an art. And the more you do, the better you get at seeing what your substitution should be. And in these first couple of examples I'm going to do, however, you're sort of forced. You're forced into your choice. What's my substitution going to be? I'm really forced here. And the reason I'm forced is because I have a composition. I know how to integrate things like e to the x, right? Or e to a constant times x. That was from our list in 7.1. But what I cannot handle is e to a function of x, right? I cannot handle these compositions. So what I need this to turn into is something like e to the u, because I can't handle anything more complicated than that. I'm forced to make this decision. So I'm forced to make this substitution. I'm going to let u be x to the 4th, so that this becomes e to the u. Alright, so that's going to become e to the u. What did we do last time in the last example? We solved for du, right? We had to figure out what du was. So du over dx, the derivative of u with respect to x, is 4x cubed. And that means that du, if I just solve for du, multiply both sides by dx, is 4x cubed dx. So what happened last time? Last time we plugged in for u, and sort of everything that was left over, x cubed dx in this case, the leftover stuff, that was what du was. Here it's not quite what du is, right? Du is 4x cubed dx. Well, that's not a problem, because I can just divide both sides by 4, right? So 1/4 times du is x cubed dx. So what am I looking at here? This is going to become e to the u, and this leftover stuff, x cubed dx, that's going to become 1/4 times du. Great. So I'll make my substitution. This becomes the integral of 1/4 e to the u du. By the way, I'm sort of splitting this. I'm splitting the 1/4 and the du apart because it's customary to write your differential du at the end. All right, but under the substitution, this is turned into this expression. And now this isn't very hard to integrate, right? To integrate a constant times a function, it'll just be the constant times the integral of that function. So it's going to be 1/4 times the integral of e to the u. And the integral of e to the u from last time, integral of e to the x is e to the x. So integral of e to the u is e to the u plus c. And the very last step, the last thing I have to do in all these problems is back substitute. I don't want my answer in terms of u. I want to go back to x. So u was x to the 4th. So here's our solution. 1/4 e to the x to the 4th plus c. And as last time, if you want to, again, this is this very nice aspect of these integration problems, is you can always check with 100% certainty whether you're right or not just by differentiating this. If I claim this is an antiderivative for this original function, then when I differentiate it, I should get this function back. And I promise you, if you differentiate it, you will get that function back. So one more thing I'll point out is maybe you're clicking through MyMathLab, you're clicking I think there's an option, show me how to do this or solve a problem that's similar to this. One thing that sometimes people do when they're teaching this material, or what MyMathLab does, is they go through, they'll find du over dx, and what I'm doing is I'm solving for du, and then I'm sort of piecing this together in a way so that what I'm left with over here on my right hand side is exactly what I'm left with when I make my substitution. Right? I'm just sort of looking at what's left over, and I'm solving for du in such a way. Sometimes you'll see people just solve for dx. Right? So if I were to do that up here, this would mean dx is du over 4x cubed. And you can do this if you want. And then when they substitute, they would just do this blindly and hope that there's no x's left over. Alright, so if you do that, you just substitute, you'd say, okay, this is the x cubed e to the u, and then dx, which I've solved for, becomes du over 4x cubed. And your hope is, and this always has to happen, this is a very common mistake with students when they're first learning this stuff, is they'll end up with integrals that have u's and x's together, mixed together. What always has to happen is you have to be left with nothing but u's. So all of your x's have to disappear, and what happens in this case is those guys cancel. And you end up where we just were, 1/4 e to the u du. And if you want to proceed that way, that's totally fine. If you want to solve for dx every single time, that's fine. Just remember that your goal is to have all of your x's cancel and disappear. I'm not going to do that. I'm going to keep sort of just working with du and manipulating it so my right hand side is what I have left over. But we'll go through more examples. Alright, integral of e to the 1 over z over z squared dz. So again, hardest part about substitution is actually figuring out what you want to substitute. It's a bit of an art, but this still isn't one of the harder ones that we're going to do because I'm forced into a choice here. Just like the last problem, I cannot work with e to a function. I can only work with e to the z or e to the x. So I have to make this choice. I have to simplify that. That has to become e to the u. So I have to choose u is 1 over z. And then I want to differentiate that, as always. I want to find du. So easiest way to differentiate 1 over z is think of it as e to the minus 1. So du dz is minus z to the minus 2, or minus 1 over z squared. And you can already see how this is going to work out nicely. Oh, I have a 1 over z squared. So this means du is minus 1 over z squared dz, which is pretty close to what I have here. 1 over z squared dz. So I'm off by a minus sign, but constant multiples don't matter. I can always fix that. Multiply both sides by minus 1, so minus du is 1 over z squared dz. So we'll go ahead and make the substitution now. This is the two steps you always go through. Choose your substitution, figure out what u is going to be, and then figure out what du is. Alright, so we'll make the substitution. 1 over z squared dz becomes minus du. I will write the minus multiplier in front, the du at the end, and then we've got e to the u. Alright, it's e to the u times minus du, so I just wrote the minus out front here. And I think we can finish this in this little bit of board space I have left, because this isn't a hard integral now. It'll be minus the integral of e to the u, which is e to the u, plus c. And we'll back substitute. U was 1 over z. So that's minus e to the 1 over z plus c. Alright, we'll ramp this up a little bit. I'm going to show you that these can get a little bit trickier in the next example. How about this? Let's do integral of x times x plus 1 to the 5th dx. This one's a little bit different than all three examples we've done so far, in that you actually can do algebra to solve this as we did last time. What I mean by that is you could just expand this out. It's a 5th power, it would take you some work to expand this out, but you could turn this into just a polynomial. And we saw last time that integrating polynomials isn't too bad. But I'm going to do this using a substitution. And again, my choice is forced. My choice is forced because I can handle x to the 5th, but I cannot handle a function of x to the 5th. I cannot deal with these compositions. So what I need to do is turn this into u to the 5th. I have to do that. So u is x plus 1 and that means du is, well, du over dx, derivative of x plus 1 is 1, so du is equal to dx. And now you'll see we have a problem. Now I go ahead and make my substitution. And what I'm going to write here isn't technically correct. I won't really write this step in the future, but I want to show you what's happening. What I have is I've got an x times a u to the 5th, and dx just becomes du. So this is bad. This is bad because your goal with these substitutions, the only way your substitutions have worked properly is if you don't have any x's left. Right? Everything should be in terms of u. Well, in this case I have an x left over. So one thing you might try to do is maybe I make a different substitution. However, as we agreed, this substitution was forced on us because I need this to turn into u to the 5th. So the other thing you can do is really just sort of force this substitution to work. I still have this x left over, but hold on, I can write this in terms of u. What I mean by that is if u is x plus 1, then what does x equal? What does x equal? X would be u minus 1, right? So I actually can write this whole thing in terms of u just by writing this as, so this line I'll never write this step again because x's and u's mixed together don't make much sense, but x is u minus 1. So this is u minus 1 times u to the 5th. And now we've succeeded. We've made this substitution. We've succeeded in making the substitution because everything's now in terms of u and just du. What sometimes happens is you'll make a substitution and it doesn't actually help, it doesn't simplify the expression at all, and this still looks pretty complicated, but in many ways it's actually much better than what we started with. Because if I just distribute this out, it becomes a polynomial. This becomes the integral of u times u to the 5th is u to the 6th, minus 1 times u to the 5th is minus u to the 5th du. And that's not a bad integral now. This isn't hard to integrate at all, right? This is u to the power is no problem at all. Just raise the power by 1, u to the 7 over 7 minus u to the 6th over 6 plus c. And that's the integral. The only thing we have to do is back substitute. Go back to x. So u is x plus 1. And I'm going to write the fractions out front. 1/7 times x plus 1 to the 7 minus 1/6 times x plus 1 to the 6th, and I can just barely fit it on the board there, plus c. And there's our antiderivative. You can check this one. You can differentiate it and check. However, if you differentiate that, I think it might take quite a bit of work, quite a bit of algebra to confirm that your derivative is actually the same as this. Your immediate derivative isn't going to look like this at all, and you'd have to manipulate it quite a bit to get to look like that. Alright, so if you're understanding this stuff, try this one. Here's a classic example. The integral of 1 over x times ln of x. The ln of x in the bottom. So pause the video here. Try and do this problem. Think about it for a little bit, and then come back. And I will tell you that this one's a bit unlike all of the ones we've done so far, because in the ones we've done so far, we looked at our expression, we saw this composition, and we said the only way I'm going to find an antiderivative is if I turn this into like u to the n. So I was forced into the choice that we made in the last few examples, just by looking at the fact that I had these compositions. Here I don't have any compositions going on. Right, there's no compositions of functions. My numerator here is a product, but I don't have a composition forcing me to simplify this. I can sort of work with all of these pieces. But still I can choose to make a substitution. And it's a bit like playing chess here. You're thinking ahead about what du is going to be when you're making your choice for u. And I'll just tell you the right choice here is to let u be ln of x. So if you're thinking ahead about what du is, and the way you can immediately see this is a good thing, is du, well, du over dx is 1 over x, derivative of ln of x is 1 over x, so du is 1 over x times dx. So I'm going to stop writing du over dx, we'll just do it all in one line. Du over dx is 1 over x, so du is 1 over x dx. And that means that this turns into the integral 1 over x dx is du, and then I'm still left with 1 over ln of x, so that becomes 1 over u. Integrating 1 over u isn't bad. This is one of our known antiderivatives from last time. Integral 1 over u is ln of technically the absolute value of u plus c. And that's the integration. Last thing to do is back substitute. U is ln of x. So this is an ugly looking function, but it's ln of the absolute value of ln of x plus c. And we could do these all day. I could do substitutions all day. I'm really good at substitutions, and the reason is because I've done so many of them. Again, it's a bit of an art, but the more you do, the more you start to see it's not so much of an art as you're forced to make a lot of decisions. And the more you do, the better you get at seeing what your substitution should be. I will do one more here before we go to a business application. Integral of x squared plus 2 over x cubed plus 6x plus 3 dx. This one's truly hard. I think if you gave this to just a random calculus student outside of the context of, okay, we're learning substitution, so it's clearly a substitution problem. I think if you gave this to a random calculus student, you said evaluate this integral, they'd probably study it or struggle with it for a little bit because it's not entirely obvious what you want your substitution to be. So what often happens, if you come across something like this where it's a complicated rational function, one polynomial divided by another, what you often want to do is just let u be the entire denominator. The hope is that I'll have something over u, and then that simplified expression will be easier to work with. So I'm going to let u be the entire denominator, x cubed plus 6x plus 3. And I'm hoping my du has something to do with everything that's left over. X squared plus 2 times dx. So my du is going to be 3x squared plus 6 times dx. So my hope was that this had something to do with x squared plus 2. It doesn't look like x squared plus 2 dx, but it actually is. It's really close. This is 3, if I factor out a 3 times x squared plus 2 dx. So not bad. I'm actually just off by a factor of 3. And if I have my x squared plus 2 dx left over, to isolate that by itself, I'm just going to divide both sides by 3. 1/3 du is equal to x squared plus 2 dx. So fantastic. This substitution is going to work out pretty well here. We've got the integral of, so we've got 1 over u, and x squared plus 2 dx became du times 1/3. And what I did in the past is I wrote the 1/3 on the inside of the integral, but one thing you could do, just to mix it up a little bit, the algebra here, remember you can always pull constants outside. So I'll put 1/3 outside the front of the integral there. And now it's no more complicated than the last example we just did, right? Integral of 1 over u is ln of the absolute value of u plus c. And the 1/3 multiplies this antiderivative because it's 1/3 times the integral. And we just need to back substitute now. Back substitute 1/3 times ln of the absolute value of x cubed plus 6x plus 3 plus c. There's our solution. All right, let's do something involving marginal. Let's see, we'll do a marginal cost question. All right, so a very similar problem to the ones we did at the end of last class, which is here we have a company that we're given our marginal cost function. This company is producing X units of a good, and the marginal cost function is in thousands of dollars, is 60x over 5x squared plus e. So the question is to find the cost function, and we know how to do that from last time. If we have marginal costs, then the cost will be the antiderivative, so we're going to integrate this marginal cost function. The problem is we'll run into this plus c when we do that, and we can figure out what the plus c is, but it's a little bit of extra information. We're told that we have a fixed cost of $10,000, even if no units are produced. Meaning, if x is 0, then c of 0 should be 10,000. In fact, c of 0 will actually be 10 because our costs are in thousands of dollars. So I'm going to have to erase, well actually I think I can just work down here for the time being. So c of x is going to be the integral of the cost function, or sorry, the marginal cost function, 60x over 5x squared plus e dx. And this is a pretty complicated looking function. I don't think any amount of algebraic manipulation will turn this into just powers of x, like a polynomial. So I'm thinking I want to make a substitution. I don't see any compositions here that are forcing my hand, but what I'm going to do is similar to the last problem, which is since I've got this rational function, I'm going to try letting u be the entire denominator. So let's let u equal 5x squared plus e. Alright, so that means du is 10x. Du over dx is 10x, so du is 10x dx. So this becomes u, and I've got 60x dx up top. So I actually want 60x dx right here. So that would mean if I multiply both sides by 6, that means 6du is 60x dx. So this is going to come du, 60x dx is du, over u. Alright, so this thing turns into the integral of du over u. And you'll see this sometimes, you'll see this written like this sometimes. This is shorthand notation though for something that might feel a little bit more comfortable to you, is this means just 1 over u times du. And the differential at the end du telling me I'm integrating with respect to u. So it's more clear to see the function we're integrating is 1 over u. So we integrate this, 1 over u integrates to ln of the absolute value of u plus c, which is ln of the absolute value of u was 5x squared plus e. Plus c. If you're very attentive here, you'll notice, wait a second, 5x squared plus e, that can never be negative, so the absolute value bars there are a little bit redundant. Not a big deal if you notice this or not, but because that expression can never be negative, I don't really need the absolute value bars. Okay, so here's my cost function. But you'll remember, I've erased it now, but there's a little bit more information given. And this isn't really the cost function because I need to figure out what c is. C isn't just some arbitrary number, it came from some actual cost function. So recall that even if no units are produced, my cost for producing 0 units is $10,000. And my cost function, my marginal cost function was given in thousands of dollars, so C of 0 should be 10. 10 for 10,000. But what happens if you plug 0 into this expression? Plug 0 into this cost function that we found, and we get ln of 5 times 0 is 0, plus E, plus C. Well, what's ln of E? ln of E is 1, right? The base, natural log, is base E. If the base and the argument match each other, you always have 1. So this gives me 10 is equal to 1 plus C. So that means C is equal to 9. Subtracting 1 from both sides. And that means, last but not least, my cost function, I've done it now, is ln of 5x squared plus E plus 9. And there's a solution. This problem is pretty much exactly the same as one we did at the end of last section, but the function is more complicated. Now it was so complicated to find the antiderivative, to find the integral, we had to use this more advanced substitution technique. Try these problems. Try doing lots of these. Go through the homework. I'll assign quite a few. The more you do, the better you'll get, but the hardest part is just figuring out what I'm going to substitute to start with. And just try things. Try making substitutions. The goal is to end up with all your x's gone. Everything should be in terms of u and du. If you don't have all the x's disappeared, then try making a different substitution. Thanks.